Добрый день. Hello, everybody. Our course will be about topological vector spaces. And the official language of the course is English. So in particular, the lectures will be in English. First of all, maybe a few words about some formal points. I'll make a web page of the course. It will be available through the website of the department. And I'll put there all relevant information, in particular a short contents of every lecture, some list of literature, of books, and exercise sheets. Exercise sheets are, of course, they are not obligatory, but they are useful. So I encourage you to do these exercises just to understand what is going on in the lectures. The grading system will be very simple. So we will have two exams. First, a midterm, and a final exam at the end of the course. And both exams will look like a written take-home individual assignment. And they will be composed of exercise sheets, of just a selection of exercises from the sheets. More details about the grading will be available at the web page of the course. I forgot to say that my name is Pirkovskii. This might, you might. Okay, so let me now say a few words about the history of the subject. The first results in topological vector spaces were obtained in the 1930s, mostly by Banach and Kolmogorov. But a systematic study of topological vector spaces began only after the Second World War, in the second half of the 1940s, first by Dieudonné and Schwarz, and later by Grothendieck, McKee, Cote, and many other people. A couple of important papers and one influential monograph are due to Bourbaki. But of the whole Bourbaki group, actually only 3 people worked in topological vector spaces, namely Dieudonné, Schwarz, and Grothendieck, who was a PhD student of Dieudonné and Schwarz. By the way, there is an anecdotic story of how Grothendieck began his mathematical career. So once a young man approached Dieudonné and said, "Professor, I want to be your PhD student." This was Grothendieck. Okay, Dieudonné answered, well, take our joint paper with Laurent Schwarz, read the paper, and at the end of the paper, you'll find a list of open problems. There are 14 problems, so just try to think about them. Okay, Professor, Grothendieck answered and disappeared for a few months. So Dieudonné and Schwarz even decided that maybe he will never come back. But one day, Grothendieck reappeared in Dieudonné's office. Well, okay, my friend, Dieudonné said, how about the problems? Have you solved any of them? Yes, Professor. And which one? I solved all of them, Professor. In fact, this legend is a bit is not exactly as it was in the real life. Actually, Grothendieck solved more than half of the problems, but not all of them. But nevertheless, this was a real breakthrough, a local, but a breakthrough in the theory of topological vector spaces. And at the same time, it was kind of a turning point in Dieudonné's mathematical career. So after that, Dieudonné almost stopped his own research and devoted himself to Grothendieck. So he supervised Grothendieck's PhD thesis jointly with Laurent Schwartz. Then they worked together with Grothendieck, and finally, when Grothendieck decided to leave functional analysis for algebraic geometry, Dieudonné followed him. The main contribution by Grothendieck to topological vector spaces is a very rich and fruitful and important theory of topological tensor products and nuclear spaces. Grothendieck himself qualified his contribution to functional analysis as very modest, and indeed his contribution to algebraic geometry is much more considerable. It was really revolutionary. But nevertheless, Grothendieck's contribution to functional analysis was very strong and important. Actually, it has a very strong impact on the development of topological vector spaces and some neighboring fields of functional analysis. It's quite instructive just to understand the importance of this contribution. It's quite instructive to look at citations at Methinet. So the number of citations of Grothendieck's PhD thesis on topological tensor products is almost twice as large as the number of citations of the fundamental book IGA, Le Monde de Géométrie Algébrique, Elements of Algebraic Geometry, written together with Dieudonné. Well, coming back to the history of topological vector spaces, the golden age of this theory was in the 1950s, 1960s, maybe the beginning of the 1970s. Nowadays, this theory is not so popular, but one shouldn't think that this theory has died. It is still alive, and many interesting papers are being published, and many nice conferences are being organized regularly. In general, the current development of topological vector spaces is directed not so much towards general theory as towards applications. Chronologically, the first area of applications of topological vector spaces was in distribution theory. Actually, this was probably the main motivation for Dieudonné and Schwartz to study topological vector spaces. And later, many other interesting applications were found in partial differential equations, in spectral theory of linear operators, later in non-commutative geometry, in quantum group theory, and in complex analytic geometry. Well, probably we'll discuss some of the applications at the end of our course. Well, probably that's all about the history. Let's now introduce some general definitions related to topological vector spaces. We'll work over the field of real numbers or over the field of complex numbers. And in most cases, it's not essential which of them is our base field. So let's use the letter bold K to denote any of them. So this is our base field. So all vector spaces will be over K. By definition, a topological vector space is a vector space over K equipped with topology. So X is a vector space, and tau is a topology on X, such that the topology is compatible with the algebraic structure in the sense that the operations, that is the vector addition and the multiplication by scalars. So these two maps are assumed to be continuous. Well, an obvious special case which you are familiar with from your functional analysis course is, of course, the case where X is a normed space. An example, and at the same time a simple exercise in functional analysis is to show that a normed space is a topological vector space. Its algebraic operations in a normed space are continuous. But of course, there are many other interesting examples. We'll discuss some of them in a few minutes. Clearly, topological vector spaces form a category. So the morphisms in this category are just continuous linear maps. So if we have two topological vector spaces, X and Y, then the set of all continuous linear maps from X to Y will be denoted by script L, X, Y. So this is the set of all continuous linear maps from X to Y. And in a special case where Y is the base field, so we obtain this vector space of continuous linear functionals on X. It is denoted usually by X prime in this theory, and it's called the dual of X. Sometimes we say the topological dual in order to distinguish with the algebraic dual, which consists of all linear functionals on X. And this is the space of continuous linear functionals. Of course, these sets are also vector spaces, but in fact, we can make them into topological vector spaces in several inequivalent ways. But at this point, we look at them as just as vector spaces. So at this point, we don't equip them with any topology. So they are just vector spaces. The axioms of topological vector space obviously imply that the topology on X is shift invariant. And this easily implies the following simple proposition. If we have two topological vector spaces X and Y, then a linear map from X to Y is continuous if and only if it is continuous at 0. Or equivalently at any other point. And more or less for the same reason, L of xy is not just a set. As I said before, it is indeed a vector space, or more exactly a vector subspace. The space of all linear operators from X to Y. General topological vector spaces are in fact too general to be interesting. So we will be mostly interested in a special case of topological vector spaces. And before define such spaces, let's introduce some more terminology. Suppose that X is a vector space, and P is a non-negative function, a non-negative real valued function on X. We say that P is a semi-norm. P is a semi-norm on X if it satisfies the following two axioms. First of all, to have the triangle inequality. So P is sub-additive. And second, it is homogeneous in the following sense. P of lambda x is the modulus of lambda times P of x. And that's it. So basically, the only difference between a norm and a semi-norm is that a semi-norm is allowed to vanish on non-zero elements. And of course, if moreover we assume that P is strictly positive on non-negative elements, on non-zero elements, then P is a norm. And the vector space equipped with a seminorm is called a seminormed space. Let's now introduce some useful notation related to seminorms. If we have an element x in our space and epsilon is a positive number, then we consider the following set, up epsilon of x, which is defined as follows. And we call this set the open ball centered at x of radius epsilon with respect to the seminorm p. Strictly speaking, I have to put quotation marks here because so far we haven't introduced any topology on x. X is just a vector space. And similarly, we can introduce a closed ball defined by a similar inequality. This number is less than or equal to epsilon. And this is the closed ball, again with quotation marks. If x is 0, we just write up epsilon. So this is a ball centered at 0. And the open unit ball of radius 1, will be denoted just up. This is the open unit ball centered at 0. Okay, so now we have the following definition. Polynormed space is a vector space equipped with a family of seminorms. So X is a vector space. And P is a family of seminorms. Every polynorm space carries a canonical topology, which is defined as follows. So the topology on X generated by P so P is a family of seminorms on X, is the topology was denoted by tau of P with the following subbase. With a subbase consisting of all open balls. P epsilon of X, where X runs over our space, epsilon is positive, and the P runs over our family, big P. So, in other words, this means that the base of this topology consists of all finite intersections of such open balls. That is, finite intersections of open balls. Intersections of open balls form a base for tau of P. So these are exactly the spaces we are mostly interested in. The topology generated by a family of seminorms can also be described a little bit more explicitly. Before we describe this topology in slightly different terms, let's make a short digression to general topology, and let's recall some terminology. Actually, there are two different points of view of what a neighborhood of a point is. So some people require a neighborhood to be open, and some don't. And we will choose the second approach. So if X is a topological space, then a neighborhood of a point in the space is a set U such that X belongs to the interior of U. So in other words, this means that there exists an open set V in X such that X belongs to V and V is contained in U. So I'd like to stress that we don't require that U is open. So U is not necessarily open. In particular, U can be closed. So, for example, a closed ball is a neighborhood of its center in any metric space. This approach to neighborhoods is quite useful in some situations related to topological vector spaces. So this is quite standard approach to neighborhoods in the theory of topological vector spaces. If I have a point X in our space, then a family of neighborhoods, a family beta X of neighborhoods of X is called a base of neighborhoods, base of neighborhoods of X, or just a base at X, if for every neighborhood U of X, there is a neighborhood V in this family, which is contained in U. And more generally, a family sigma X of neighborhoods X is a subbase of neighborhoods of X. If finite intersections of neighborhoods in the family form a base of neighborhoods of X. So this family is a base of neighborhoods. Well, for example, if you take any point in the plane and consider all half planes containing this point, for example, the origin, all half planes containing the origin form a subbase of neighborhoods of the origin. Because if we intersect 4 half planes, then we get a square, and it's well known that squares containing the origin form a base of neighborhoods. Let's now come back to polynorm spaces and do some more notation. If X P is a polynorm space, and if we have an element in X and finite and many seminorms P1 to Pn in our family, and the positive epsilon, then we can consider the following set indexed by our seminorms and positive number epsilon. So this is just the intersection of the respective balls, U, Pi, epsilon, from 1 to n. So it consists of all y such that we have the following inequality. This is less than epsilon for every I from 1 to n. And we have the following simple proposition. First of all, I claim that if we take any point in X, then the family of all open balls centered at X is a subbase of neighborhoods of X. Of course, these neighborhoods are open just by definition of our topology. And similarly, if we consider all sets of this form, P1 to Pn, epsilon of X, where P1 to Pn are seminorms from our family, n is natural, and epsilon is positive, and this is the base of neighborhoods of X. And similarly, if we now let X run over the whole space, then we get the base of the topology tau of P. So this family is a base of tau of P. This is almost immediate from the definition of our topology, but not entirely immediate, because formally, if we look at the definition of our topology, so finite intersection of such balls form a base for the topology. So formally, to construct a subbase of neighborhoods of a point, we must consider all open balls containing this point, but probably with a different center. But it's a simple exercise. By using triangle inequality, we can show that any open ball containing X contains a smaller ball centered at X. This is a simple exercise, which follows from the triangle inequality. So the proof is given by this picture, if you like. So the details are just an exercise for you. Okay. Another useful description of the same topology looks as follows. This is just a simple observation. So for every seminorm P from our family, let X sub P denote the space X equipped with the seminorm P. So we look at the space as a seminorm space with respect to P. So we forget about all other seminorms from our family and remember only one of them. So the observation is that the topology tau of P is the weakest topology on X. Weakest, I mean, the coarsest topology on X, such that the respective identity map from X to XP, so denoted by ID sub P, is continuous for every P. So this is immediate again from the definition. So if we want to construct such topology, then of course all such sets have to be open in this topology, because they are open here. So their privileges will be open here. And if we define our topology in this way, clearly this topology will be the weakest topology, the coarsest topology with this property. And so this implies that for every topological space Y, we have a map F from Y to X, then this map is continuous for the topology of P, even only if the composition with this map IGP is continuous for every P. Okay. By the way, a little remark about this notation. It's by using this proposition, it's very easy to show that the closed ball, defined in this way, is indeed closed and is equal to the closure of the open ball. We'll use this result sometimes, so this is a simple exercise for you. Set is closed, and moreover, it is the closure of the respective open ball in the topology of P. Okay, so now in summary, we see that any polynorm space, has a canonical topology, and at the same time, it's a vector space. So the initial question is it a topological vector space? And the answer is yes. Simple proposition. If we start with a polynorm space, X is a polynorm space, then it is a topological vector space for the topology generated by P. Well, formally we have to check the continuity of the algebraic operations, and of course this can be done in a straightforward way, but probably the most elegant way to show this is to reduce everything to the case of semi-norm spaces. For example, if you want to show the continuity of multiplication by scalars, we can do the following trick. We fix a semi-norm from our family and consider the following diagram. So this is our map IG sub P. This map. We have a similar map here. This map wants to be continuous. We just use this criterion. So to prove that this map is continuous, we have to show that this composition is continuous, as the diagram is commutative. So we have to prove that this map is continuous, and everything follows from the case from the statement that from the result that the multiplication by scalars is continuous in the case of a polynorm of a semi-norm space. But for a semi-norm space, this result is well known, and it is proved in exactly the same way as in the case of norm spaces. So this map is continuous, like in the case of norm spaces. And the diagram implies the continuity of this map. And similarly, we prove the continuity of addition. Okay, so every polynomial space becomes a topological vector space. And it is exactly this kind of topological vector spaces we are mostly interested in. A nice feature of such spaces is that when we work with such spaces, we have basically two equivalent languages at our disposal. We may use the language of general topology, that is open sets, neighborhoods, and so on. And very often, in fact, almost always, we can replace this language by the language of semi-norms and certain inequalities between semi-norms. And sometimes this is very useful. In general, two languages are always better than one. Here's a simple illustration. Position. a polynomial space equipped with the topology generated by a family of seminorms P is Hausdorff. It's Hausdorff, even only if for every non-zero element in our space there is a seminorm in our family such that P of x is strictly positive. And the proof is very easy modulo this description of a subbase of neighborhoods of any point. Well, indeed, to prove the left-to-right implication, observe that if this statement is not true, if all seminorms vanish on X, then X actually belongs to every neighborhood of 0. Otherwise, if this is not true, then X belongs to every neighborhood of 0. And of course, X is not Hausdorff in this case. Well, indeed, if all seminorms vanish on X, then X belongs to every open ball centered at 0. But since such balls form a subbase of neighborhoods of 0, it follows that actually X belongs to every neighborhood of 0. And to prove the right to left implication, we take 2 points, X and Y, such that X is not equal to Y, and find a seminorm in our family such that P of Y minus X is, as noted by D, is strictly positive. And then we can easily construct 2 disjoint neighborhoods of X and Y. Namely, we can take open balls with respect to the seminorm P of radius D over 2. So the triangle inequality easily implies that these 2 balls are disjoint. And so our space is Hausdorff. Well, another result which interprets topological property in terms of seminorms is as follows. A sequence xi in our space converges to a point level x, even only if it converges with respect to every seminorm, in the sense that P of xi minus x goes to 0 for every P in our family. Well, this is also very easy, so the proof is an exercise for you. Okay, so let's now look at some basic examples of polynomial spaces. The first example is the space of all functions on any set. So we take any set X and consider the space of all k-valued functions on X. All functions from X to K. We can define a family of seminorms on the space as follows. For every point in our space, we define a seminorm indexed by X, as denoted like this, by the following simple formula. So the seminorm evaluated at function f is just the absolute value of f of x. By the way, a few words about our notation. So when we work with seminorms, sometimes we denote our seminorms by Latin letters like P, Q, R, and so on. And very often our seminorms will be denoted by such a symbol, so like a norm, but with a suitable subscript, which runs over a suitable index set. Sometimes it is quite convenient. A simple exercise is almost an observation, is that the topology on our space generated by a family of all such seminorms indexed by points in our space is nothing but the product topology on the space. It's the product topology on our space. So just recall the standard definition of the product topology and observe that it is exactly the topology given by this family of seminorms. Sometimes this topology, in this case, sometimes this topology is called the topology of pointwise convergence. The topology of pointwise convergence. And the reason why it is so called is that if we look at this proposition, we see that a sequence fi converges to f in our space, even only if it converges pointwise. The next example is the space of continuous functions on the topological space. Example 2. Suppose that X is a topological space. Then we can do the following. We can take any compact subset K of X. And we define a seminorm on the space of continuous functions, which will be denoted like this. So it is indexed by a compact set. As follows, we just take the supremum of the continuous functions of a continuous function f over k. Well, f is continuous, so it is bounded on any compact set. So we can take the supremum. So we obtain a family of seminorms on C of x indexed by compact subsets of x. And this family seminorms, so we runs over all compact subsets of x. The family generates the so-called compact open topology. Compact open topology on C of x. Which is sometimes called the topology of compact convergence. The topology of compact convergence. And again, an explanation for this terminology comes from this proposition. If we look at a sequence of continuous functions on x, then it converges for this topology, even only if it converges uniformly on every compact set. Fi converges to f in C of x, even only if it converges uniformly for every compact subset k of x. So this is the standard topology on the space of continuous functions. Example 3, let's now look at the space of smooth functions. First of all, in the case where the functions are defined on the closed interval of the real line. So the standard topology on the space is defined as follows. For every non-negative integer m, we define a seminorm on our space, C infinity of AB, as follows. This will be the supremum of the nth of the modulus of the nth derivative of f over the interval. If m is 0, then this is just the uniform norm, the usual supremum norm on our space, but we consider not only the supremum of our function, but also of all its derivatives. So we get a sequence of seminorms, and by definition, the standard topology on C infinity of AB is the topology determined by, generated by a family of all such seminorms. So M runs over all non-negative integers. Again, if we look at this proposition, we see that the convergence in this topology is the uniform convergence with all derivatives. I converges to F in our space if and only if every derivative, Fi, the nth derivative converges uniformly to the nth derivative of F for every F. Let's now consider a case where we still deal with simple functions, but now not only on a closed interval, but on an open subset of Rn. This is example 4. So we take an open subset of Rn. And we want to define a topology on C infinity of U, on the space of smooth functions on U. To define this topology, it's convenient to use the standard multi-index notation. So if we have a multi-index alpha, that is an n tuple of non-negative integers, and a smooth function f from U, we denote by d alpha of f the following partial derivative of our function. And for every compact set K in U, and for every alpha, we define a seminorm indexed by K and alpha on the space of smooth functions as follows. We take our function and we calculate the supremum of the respective partial derivative, the alpha of f, over K. So clearly this is a seminorm of our space. And by definition, the standard topology on C infinity of U is the topology generated by the family of all such seminorms. K alpha, where K runs over the family of all compact subsets of X, and alpha runs over all multi-indices. Again, it's very easy to describe the convergence in this space. So a sequence Fi converges to F in C infinity of U if and only if it converges uniformly on every compact set with all partial derivatives. The alpha Fi converges uniformly to the alpha of F for every alpha and for every compact set. A nice exercise is to generalize this construction to any smooth manifold. An exercise. So define a reasonable topology on C infinity of M, where M is a smooth manifold. possibly with a boundary. We can either take a suitable atlas on X, but in this case we have to prove, we can do the same thing, but we have to prove that the topology, the resulting topology is independent on the choice of this atlas. Or we can do something more invariant using vector fields. Another example, example 5. Example 5 is the space of holomorphic functions. So now we suppose that U is an open subset of Cn. And we consider the space script O of U of holomorphic functions of U. If you're not familiar with holomorphic functions of several variables, you will easily assume that n equals 1. This case is also quite interesting. So the standard topology on the space is just the topology induced from C of U, that is the topology of compact convergence. Topology induced from C of U. But another description of this topology can be given as follows. This is an exercise. We can consider O of U as a subspace in C infinity of U and take the induced topology from C infinity of U. And it turns out this topology is identical with the standard one. This topology is equal to the topology induced from C infinity of U. Our next example is the so-called Schwarz space, which is a very important object in many areas of mathematics and mathematical physics. In fact, I forgot to tell you at the very beginning that the theory of topological vector spaces has important applications not only in mathematics but also in quantum mechanics and in quantum field theory. Example 6 is the Schwarz space. Schwarz space. It is defined as follows. The space S of Rn, strip S of Rn, consists of those smooth functions phi on Rn, such that for every pair of multi-indices alpha and beta, the function x to the power alpha times the respective partial derivative of phi is bounded on Rn. Here, x to the power alpha is a standard notation for the respective monomial. So in other words, our function and all of its partial derivatives are rapidly decaying at infinity. So if you multiply it by any monomial, the resulting function is always bounded. The standard topology on the space is defined as follows. So for every pair of multi-indices, alpha and beta, we define a seminorm indexed by this pair, alpha and beta, on the Schwarz space by the following simple formula. This is just the supremum of this function over Rn. Space. So the standard topology on the Schwarz space is given by the family of all such seminorms. So this topology is generated by all seminorms of this form. By the way, if you take some standard textbook on topological vector spaces or on functional analysis or mathematical physics, you may find a slightly different definition of this topology. And indeed, there are several versions of these seminorms. For example, we can replace here the monomial by something like the norm of x to the power k, or we can even integrate over the whole of Rn and take the respective L2 seminorm. So these seminorms are different, but we will see shortly that they then define the same topology on the Schwarz space. So we can generate the same topology by many different families of seminorms, and this is quite a typical picture. In some situations, this family of seminorms is more convenient, but there are situations in which L2 seminorms on the Schwarz space are more useful. Our next example is a discrete analog of the Schwarz space, example 7. This is the so-called space of rapidly decreasing sequences. Rapidly decreasing sequences. So this space is denoted by a little s, and it consists of all sequences xn indexed by natural numbers, such that for every non-negative integer k, the sequence xn times n to the power k is bounded. Again, this means in some sense that our sequence is rapidly decreasing. So after we multiply it by n to the power k, whatever k is, the resulting sequence has to be bounded. And the family of seminorms, the respective family of seminorms, which generates the topology on the space, is defined in much the same way as in the case of the Schwarz space. And we just take the supremum of the sequence for every k. So we define seminorm indexed by k on S to be the supremum over n of the sequence. And the standard topology on S is given by all seminorms, is generated by all seminorms of this form. It turns out that the space is rather important for many reasons. In particular, it can be shown that actually many standard functional spaces, which appear in different fields of mathematics, are actually isomorphic to little s. For example, the Schwarz space is isomorphic to little s, in spite of the fact that the isomorphism is not obvious. It involves Hermite functions, but nevertheless they are isomorphic. And there are many results of this kind, mostly due to the German mathematician Dietmar Vogt. In particular, he proved that if you take a space of smooth functions on any compact real manifold, so this space is always isomorphic to little s. This is not obvious at all, but it turns out this is the case. Okay. Our final examples for today are most probably they are familiar for you from your functional analysis course. Example 8 if we take any topological vector space, X, for example, it can be a norm space, then we define the weak topology on X to be the topology generated by a family of seminorms indexed by continuous linear functionals on X, where such a seminorm is defined as follows. If X is an element in our space, then our respective seminorm evaluated at X is just the absolute value of f of X. So we get a new topology on X, which is called the weak topology. And the reason why it is called weak is that it is indeed usually weaker than the original topology on X. And the related example is the so-called weak star topology. Example 9. If X is a topological vector space, then the weak star topology of the dual on X prime is the topology generated by a family of seminorms indexed by elements of X, where the respective seminorm is given by the following formula. This is just the absolute value of f of X. In other words, this is exactly the topology induced from the space of all functions, of all k-valued functions on X. The topology induced from k to the power x, from the space of all k-valued functions on X. Okay, so probably that's all for examples. We'll need some more advanced examples in due course. And now, our next strategic goal is to give a geometric description of polynormable spaces, that is, of those topological vector spaces whose topology can be given by a family of seminorms. So before we give such geometric description of such spaces, let's discuss some notions related to convexity in vector spaces. Some notions related to convexity. So suppose we have a vector space. X is a vector space, as usual, over K, over the real numbers, or over the complex numbers. And suppose that S is a subset of X. So I'd like to stress that at this point, we don't equip X with any topology. So this is just a vector space, a pure algebraic object. We say that our subset S is convex. Probably you are already familiar with this notion. We say that S is convex if for any 2 points X and Y in S, the interval from X to Y is also contained in S, where the interval X, Y consists of all points of the following form: Tx plus 1 minus Ty. The second definition, we say that S is circled or balanced if for every X in S and for every number lambda such that the absolute value of lambda is less than or equal to 1, we have that lambda x belongs to S. So in other words, S is circled or balanced if it is stable under multiplication by scalars such that the absolute value of lambda is less than or equal to 1. And finally, we say that S is absolutely convex. Absolutely convex if it is convex and circled. The Russian for circled is закругленный. Another example, if P is a semi-norm on our space, on X, then any open or closed ball centered at 0, UP or UP bar, they are absolutely convex. This readily follows from the triangle inequality. Let's now observe that if we take any family of convex sets, then the intersection of this family is also convex. The intersection of a family of convex sets is also convex. And the same is true for circled sets and for absolutely convex sets. Absolutely convex sets. And this observation naturally leads to the following definition. For every subset S of X, we may define the smallest convex set containing X. It is called the convex whole. The convex whole of S is defined to be the intersection of all convex subsets T of X which contain S. So clearly this is the smallest convex set containing S. And similarly we may define the circled whole circled whole of S, which will be denoted like this, and the absolutely convex whole, the absolutely convex whole of S, and the standard notation for the absolutely convex whole is gamma of S. So the definition is similar. This is the intersection of all absolutely convex sets containing this. All these wholes can be also defined more explicitly as follows. So we have the following proposition. The convex whole of S consists of all convex combinations, that is, linear combinations of the following form, where xi are elements of S, lambda I are non-zero numbers, such that their sum is equal to 1. And n is an H operator. The circled whole of S consists of all elements of the form lambda x, where lambda is less than or equal to 1, and x runs over x. And finally, the absolutely convex hull, gamma s, consists of all linear combinations of elements from our set, where xi belongs to s, lambda I belongs to k, and such that the sum of the absolute values of the numbers lambda I is less than or equal to 1. Well, the proof is rather straightforward, so this is an exercise for you. The description of the convex hull is more or less standard, and 2 is very easy, and 3 easily follows from 1 and 2. As a corollary, we obtain the following useful result. Namely, if S is circled, F is circled, and so is the convex hull of S. This is a simple corollary from this formula. So if S is stable under multiplication by such numbers, then we can simply multiply the whole combination by the same number and stay in the convex hull. So convex hull is also circled. And 1 easily now already implies the following. So for every subset S of x, the absolutely convex hull of S can be defined as the convex hull of the circled hull of S. This easily follows from 1. So clearly the right-hand side is contained in the left-hand side, but 1 implies that the right-hand side is actually absolutely convex, and so these sets are the same. By the way, we cannot here, in general, we cannot interchange the convex and the circled hull. So if we interchange them, then we usually get something smaller. Okay, now one more definition. Suppose we have two sets, S and T, in our vector space X. We say that S is absorbed by T, or equivalently we say that T absorbs S. If there exists a positive number C, a positive constant C, such that S is contained in lambda T, whenever the absolute value of lambda is greater than or equal to C. Поглощает. S поглощает. No, sorry, just the other way around. S поглощает S, а T поглощает S. S поглощает S. T или T поглощает S. And we say that a subset S of T is absorbing if it of S of X is absorbing if it absorbs every point of X. Every point of X is observed by S. By the way, let's introduce some special notation for this situation. So if S is absorbed by T, we'll write such a symbol like an inequality, but curved. So this means S is absorbed by T, or T absorbs S. A typical example of an absorbing set is a neighborhood of 0. Example and exercise at the same time. If X is a topological vector space, then every neighborhood of 0 is an absorbing set. So this is true because X belongs to lambda U, so we want to show that for every X, X belongs to lambda U is lambda is big enough. But this is equivalent to the following: X lambda inverse X belongs to U. And this is true if lambda is big enough, because this vector converges to 0 by the continuity of the multiplication. So if lambda goes to infinity, then 1 over lambda goes to 0, and this vector also goes to 0 because of the continuity of the multiplication. And so it is in U if lambda is big enough. So this is true. If the absolute value of lambda is big. So, in conclusion, let's now introduce an important concept, namely the Minkowski functional of an absorbing set. If S is an absorbing set subset of X, then we define the Minkowski functional of S as follows. This is a function P sub S, and a negative function on X, given by the following formula. This is the infimum of all non-negative numbers lambda, such that X belongs to lambda S. So since this is assumed to be absorbing, we see that this set is non-empty. So there exists such a lambda that X belongs to lambda S. So this definition makes sense. This is indeed a non-negative real-valued function of X. And here's a typical example and an exercise at the same time. If we start with a seminorm, if P is a seminorm on X, then the Minkowski functional of the respective open unit ball, as well as the Minkowski functional of the respective closed unit ball, so they are equal to the original seminorm P. Okay, so that's all for today. Let me just say a few words about our future plans. So why do we need all these geometric notions? So our next goal will be as follows. We want to show, and this will be one of the first results on the next lecture, that a topological vector space is polynormable in the sense that its topology can be determined by a family of seminorms, if and only if it is locally convex, which means that there exists a base of neighborhoods of 0 consisting of of convex sets. Locally convex means that we have a neighborhood of 0 consisting of convex sets. Equivalently, we will show that these sets can be taken to be absolutely convex. This is an equivalent definition. And an explicit construction will be as follows. If a topological vector space is locally convex, then first we construct a base of neighborhoods of 0 consisting of absolutely convex sets. And then for each such neighborhood, we consider the respective Minkowski function. And we will show that the Minkowski function, in this case, it is indeed a semi-norm. And moreover, the family of all such semi-norms, which are constructed out of a suitable base of neighborhoods of 0, determines the same topology. So as a result, we see that every locally complex topological vector space is polynormable. That is, its topology can be given by a family of semi-norms. Okay, thank you. That's all for today.